是什么东西
OK，
一个是我问这一个 different movement 的 role，怎样 describe 这一个 spec？也是这边讲说，比如说 Stephen 是从 experiment 那边找到这样子一个 relation，then Mossman 他从 thermodynamics derive 到 intensity related to temperature。
OK，
如果我们现在这样子写，然后这边有 energy density per frequency，它可以 relate to intensity。
怎样 relate？
像 energy 的话就一哦，unit frequency 这边是这样，然后intensity 是我这边就是 energy per time，还有用些 relation，那个是一个我想要的水的energy。
OK，这里有 intensity，I 就是 P over A。OK， so 你是说 E 等于 P over A 整体？
是 P over T，对 P over A，P over A。
对，是吧？E over AP 的，so E 就等于E 就等于 E over T 或者 T over I 了，对吧？T over I，你能讲呀？E 就是等于 AIT 吧，E 等于 AIT 啊，说 energy 跟 intensity 是
不过是这个我在看回去有
可是 T 不是 fix 的 T 不是 fix 的，
它是 measure 的 time，所以呢，我们的 frequency 是 wave 的 frequency。
I mean 不是没有 proportional 的话 like 我这个 proportion 呢，这个的话应该是这个意思，proportion 的意思。
这个是我讲的，
这个是 constant 的，相反一个是 constant 的，所以如果把 U 写成 AIP 的话，所以这两个是 constant，A 是 constant。OK，嗯，那可能不是，因为这个是可 T 啊，对不对？这个是它的 variable。
哦，frequency 是讲它的 wave of frequency，它的是我们在 certain time measure 到的。
对，没有，我在很最 confused 的是这两个是吧？Like 这个应该是 constant 嘛，说如果你要讲它 directly proportional to 的话，应该这两个 constant 嘛，对不对？Area 应该是 constant 啊，因为你的 experiment 这个可是这个 T 是 per time，应该不是 constant 吧？嗯，
但是这边是的，
对啊，
应该不是 constant 吧？
所以那个 proportional 的 relation 是这样。
再 check。
Yeah，可是它不是 directly proportional。Testing. All right, we'll just start. Hopefully we can finish much of the commutative algebra this week, and then we can start with affine varieties. By the way, the assignment is out already. Have you tried it? Have you looked at it yet? Okay. Or maybe tomorrow I'll ask again, see if the deadline is feasible or not. Okay, if not, you aim for this Friday first and see how it goes. Any other thing? So I think there's one more group haven't make appointment with me, right? Hey, Jung Hong is not here. Where's the Jung Hong group member? How you guys decide? Have you guys met? Not yet met. Not yet met. You didn't find your master? Huh? You already found master? No. Yeah, you group with him. Have you guys communicate? Huh? No. So how? Huh? After class? Yeah. Huh? Do you guys have a group? Do you guys have a group chat? Okay. And then what do you mean by pretty responsive? So people are answering.
So I just the group as a group leader, just follow the track.
Well, I mean, without group leader, you also need to meet, right? So, you guys gonna meet me this week? I think I only have one time left. I think it's Wednesday, 9 o'clock. Ask your group member can see me or not. And then you guys should meet before me once. 9 o'clock is your time? Let me see. Yeah, 9 p.m. I think I only have one Wednesday, 9 p.m. this week to meet. Try chat in your group if all of you can make it or not. And then try meet at least once before meeting me. Okay? Okay, no. Yeah, not a single responsibility here. Everyone should be responsible to me. Okay, so let me know again. All right, everyone see? Okay, so let's recall the definition we introduced last time. In particular, let's talk about irreducible element and prime element again. So what does element to be irreducible mean? How about Jack? What does irreducible element means? Sorry, is a unit or is not a unit? If it's a unit, then nothing to discuss already, right? Do I need a, huh? Sorry? A is not unique. And one more property. Hmm. If it is just not a unit, also trivial, right? Why I need a new word? One more. 嗯，去找一下。我可能盯在那边不会盯整天。saya what's the other property？去找。If you don't have a definition in your mind, right, it's pretty hard to prove stuff or talk about things. Okay. What's the other property? Uh, Larry. Mhm. Okay. So if you can write it as a product of two things, then either one of the term must be a unit. Okay. It itself is not a unit, but if you write it um, in a product of two things, one of them must be a unit. Second, how about prime element? Okay. Uh, 精神, what is the prime element? Hmm. A is what? Divide what? A divide itself. You mean prime number? Like a prime number? Either A divide A or A divide either one divide A. That's not the definition we take here. So the definition we take here is similarly we start with A is not a unit. And whenever A divide B, C, then either A divide B or A divide C. Okay, so well, you could try and take the prime number definition, see which one implies which. And see which implies which. Okay. So this is not quite the prime number definition yet. Actually, you can see here, prime number is more like an irreducible element. Okay. So there are more subtle property on these prime number. It's not just the dividing, it's the property being irreducible. Okay. So please don't confuse. Maybe I'll make a tutorial question on that. By the way, I also released 2 tutorial already. So try and do it. If you do it, you can kind of discuss with me. If I got time, I'll have our solution. Depends. And last time we discussed about 2 segments, right? Not all the irreducible elements are prime, and not all the primes are irreducible. Okay, I gave you 2 counter examples. And now we're gonna prove that in a integer domain, actually a prime element is necessarily irreducible. Okay, so this is what we briefly say just now. An irreducible, a prime number is irreducible. Okay, because Z is an integral domain. Okay, so let's prove this. Okay, so this kind of proof, algebraic proof, is really simple. So what do I mean by simple here? I didn't mean it's very easy. Simple means here you just spell out the definition. Okay, you just spell the definition here. So what's the things you need to show? You want to show that a prime element is necessarily irreducible. Okay, so well, you need to show for all prime, right? So just take an arbitrary prime. Okay, in R, an integral domain. You want to show that it is necessarily irreducible. Okay. So again, what is irreducible mean, Jack? Okay. Is what you need. Okay. So now, first thing, is A not a unit or not? Correct, right? Because P, sorry, did I give it a name? So let's give the name A. Okay. It is not a unit because a prime is not a unit by definition. Or by assumption, it is not a unit. So now you need to assume that what happened if A equals to BC? So if A equal to BC, obviously A divide BC because A equals BC times 1. What's the definition again? So one of them is a unit. Okay. So we want to show that B or C is a unit. So meaning what? You want to find a multiplicative inverse to B or C. Okay. Based on these 2 property here, can you do anything or not? You haven't used the assumption, right? Assumption still have one more property you can use, right? Either A divide B or A divide C. Okay. So without loss of generality, we don't know which one is true. So we might as well assume A divide B. Okay. So if A divide C doesn't matter or not. Without loss generality here, there's some argument hidden here. So if let's say actually A divide C, what can you do? You just sort the labeling C and U. Okay. So we may assume A divide B. So we can write B equals to R times A for some R in a ring. Okay. Then what else we can do here? You know your B has a new form already, RA. we can rewrite our A. A equals to A R C. Okay. Well, I think the ring we consider here is commutative. So we can simply solve commutative ring, commutative algebra. But what can you do here? A is not a unit. Can you cancel? So you can yes. Yes. How? A is not unit. There's no A inverse. How to cancel? Those who just take A1 should realize something here. Sorry? Use what? Distribute? How to distribute? You sure distributing is saying put A to the other side? Okay. Okay, you want to do this A minus ARC, and then you want to distribute. And then okay, is equals to RC. What happened? Sorry, YC is your unit. Y the inverse is R. Y1 equal to RC. Why? Huh? Why RC equal to what? Huh? Identity? What identity? Huh? I mean, I'm asking why RC equals to what here? Huh? Is the domain. Domain says what? So because we are in the integral domain, either A equals 0 or 1 minus RC equals 0. Then why 1 minus RC must be 0? Huh? Because A is not equal to 0. Why A is not equal to 0? Because A is a prime. Okay. So since A is not 0, as it is a prime, and R is an integral domain, 1 minus RC is equal to 0, which implies that 1 equals to RC, and then R is the multiplicative inverse. Actually, what's the law we use here? This is the cancellation law. Okay, cancellation law in the integral domain. Although you don't have the inverse for A, you still can cancel it out. Okay, no. Well, either one of them get cancelled, depends. Well, that's not what I want to say. I want to say from here actually, A equals to ARC here. Okay, you can cancel A from both sides. Okay, continue. So R is the multiplicative inverse of C. Okay, so this one I'm very standard ring theory argument here. Okay, the other one is here an irreducible element in a PID is prime. Okay, so you have the other direction if you are in a PID domain here. Okay, so meaning if the ideal is always principal, then the irreducible element and prime is actually the same. Okay, that's why you see that prime number have these two property holding. You know, Z is a principal ideal. Okay, so prime number have these two properties. So in general ring, you don't have these two property close together. You know, I gave you an example already. Not every irreducible is a prime. Not every prime is irreducible. Okay, so let's do similar ring argument here. What do you do? Well, how do you start? Hang Wei. Good. So let's take an irreducible element. A in a PID. Let's call it R. Okay. Well, it's not unique. Okay, so no need to talk about it anymore. So let's go to the real case here. Let's suppose A divide BC. Okay. To show that it's prime, what do we need to show again? A divide BC implies either A divide A, B, or A divide C. I think this is a good not problem. B. Okay. So we need to use PID condition. No? We need to use irreducible condition here. Okay. Let's see. Yeah. So let's consider the ideal generated by A and B. Okay. As R is a PID, okay, what we have is this ideal is actually principal. Okay, so meaning it is generated by some elements D. Okay, I don't know what is D. D could be A, could be B also can. I don't know. Depends. Okay, doesn't matter. But now in this case, D will divide A and divide B as well. Okay. So if it divide A, we can write A equals to DE, for example. Okay, for some E. So you see, we write A equals to some product. But A, like Hang Wei said, is irreducible. Okay, so meaning what? As A is irreducible, then either what? I can't pay. Irreducible definition. Either either what? D unit or E is a unit. Okay. So if D is a unit, what does it mean? The ideal generator is a unit ideal. Meaning what? The ideal generated by AB is the whole ring. Okay. So if it is a whole ring, then we can find one inside the ideal. Okay, I can write one as a combination of, can I say linear combination? I'll just say a linear combination of AB. Okay, just combination. Don't want to use linear. There's a power issue here. In particular, okay, we can use this to make C actually. We can write C as C times C lambda A plus C mu B. Okay. But what do you have here? A for sure will divide, not that. A will divide C lambda A. Okay. A is equal to what? A divide BC. So obviously A also divide mu BC. Okay. But if you divide the combination, right, you will divide A also, as C. Okay. Okay. No. Yeah. Okay. Because, for example, you write it as A times sum E plus A times sum D. Okay, so you can write it as a multiple of A. Shouldn't use C. D also used before, use G. Okay, so this is a very standard argument you can see when you learn number theory divisibility. Okay, A divides C. Okay, so this is one possibility. So A divides C. If A divides C is good. If on the other hand, if E is a unit, what happens? If E is a unit, what happens? Since A equals to DE, right? A equals to DE, we can write D as A times E inverse because E has an inverse. But this means what? This means A will divide D. Then D is a multiple of A. What else we know? Anything else we know? So from this ideal here, right, D divides A, D also divide B. Correct? No? Okay, because you're gonna make B from D, because this ideal is a principal ideal. D will generate everything. Okay, so not that. We have also D divides B. Okay, so in this case, what can you see here? A divide D, D divide B. So by transitivity of divisibility, 2 divide 4, 4 divide 8. So 2 divide 8. You can see A will divide B. Okay, so in both cases, either A divide C or A divide B. So this shows that A is okay or not? Okay. Okay. Okay, so I think algebra proof have a very nice property. You just list out all the possible case and then you will see what happens. Okay. Any question so far? Good question. Okay, next is the thing that we skipped last time. Now we're gonna show that every PID is Noetherian. Then this will show that all Z, all the field, for example, not field, all the ring, for example, the integer, and then the field, and then field join X. Okay, these are all Noetherian because they are PID. So let's prove it. Okay, so what's the Noetherian property means again? If you have an ascending chain, the chain must terminate. Okay, so we're gonna use that definition. So let R be a PID. Let's suppose we have a chain. We must start with a chain to show that it terminates. What's the special about this chain of ideal? This is an ideal in PID. And what's special about the ideal here? What's the form of the ideal here? Sorry? Who said something? What's the form of the ideal here? It's principal, right? Okay, generated by one single element here. So let's say generated by A1, generated by A2, A3, and then so on. Okay. So what's the trick we're gonna play here? Who is the terminator here? Huh? Who's the terminator here? What's the terminator here? Uh-huh. Oh, you use that. Okay, okay. Also can. Also can, yeah, also can. Also can if you use a finally generate anything. Reduce generate. Yeah, also can. Huh? Huh? Sorry? Uh-huh. Uh-huh. Yeah, yeah. I mean, if you use the other definition, equivalent definition, you can just say that every idea is generated by one element. Yeah. Let's say if we want to start with this, what do you do here? Okay, so yeah, sure. You can use the union of ideals. You can look at the unions of ideals. I think this is one of the technique we saw last week, right? You can union all the ideals together. Okay, it's again an ideal in R. Okay, so there exists another element in R such that this union is generated by one single element. Okay, but for sure, this B here will live in one of the AN. Okay, live in one of the AN. Then this is the N you stop. The first place you see this N. You can find the first place or second place also doesn't matter. But I mean, if you want to be precise, I cannot say precise also. It depends what you want. Okay, so if you found the first place where this N happens, well, you can just stop there. Okay, yeah, you can just stop there. Yeah, just now a very good point pointed out by Wei just now. You can use every ideal that's finally generated to prove that all the PIDs are bacteria. But last time when we talked about that examples, right, we haven't shown the have we shown that? I think have we shown? I think we haven't shown the equality yet, equivalent statement. But once we have the equivalent statement, then you can freely use any one of them. Okay. Yeah. Okay. Let's continue. Okay. Next proposition. In a PID, every non-zero element can be factorized into a product of irreducible elements. Okay, so it's like a row of prime number in integers, the prime number factorization. Sorry, yeah, PID is a UFD. Yeah, later we'll see. So this is like irreducible factorization in a PID. So in prime number, in integer, you have prime number factorization, right? And in here, you have irreducible factorization. Okay, so how are we gonna prove this? Okay, so how are we gonna prove this? So you see, it might feel weird. I put a Noetherian property in front here. So in mathematics, right, usually when we introduce in sequence, right, we must use what we introduce. Okay, so somehow we need to use a Noetherian property of PID to prove this. Okay. So for example, this kind of existence proof, right? Give you an element, write down the product, give you an element. Existence proof is kind of tough because your factorization might differ with different elements. Okay, so what we're gonna do here is suppose it cannot. Okay, so to give us more room to play, okay, more assumption. Okay, we do contradiction or contrapositive. So suppose not. Okay, suppose not means what? So this means that let's say we can factorize it, okay, but one of them is not irreducible. Okay, so let's say we can factorize it, but one of them is not irreducible. Then, since it's irreducible, right, we can further factorize it. So meaning I want to factorize, let's say A1. Maybe B1 is also not irreducible, but that's not a point. Let's say I know one of them is not irreducible. Then I can further factorize it. And this factorization, right? So this is a key here. Okay, this is a key to infinity here. So one of them is also not irreducible. Because if it is irreducible, I just put everything back. Then I can split it as a product of irreducible already. Okay, so suppose one of them is not irreducible again. Okay, so what can you see here? We can continue the process. Okay, because if not, if you cannot continue, that means I can put all of them back such that it could be a factorization of irreducible element. Okay, but we started with we cannot write it as a product of irreducible element. Okay, so we continue to split it. So let's continue the argument. Continuing this argument here. What do we get is we keep splitting up our reducible non-stop. Okay. And so on, such that each AI is not irreducible. Okay. So what we have here is we actually have constructed a sequence. So this sequence is like A, A1, A2, A3, and so on. Okay, such that we have a increasing chain of ID. Okay, but this idea must stop, right? Okay, so if you have a non-stop one, this will contradict a Noetherian property of PID. Okay, so the story is if you cannot split it into a product of irreducible elements, then these elements will form these terms inside the product will form a non-terminating ascending chain, okay, contradicting the Noetherian property. Okay. Question? Any question? Yes. Cannot understand why it non-stop. Let's say it stop, then your A can be written as a product of irreducible elements here. Okay, if it stops somewhere, okay, if stop somewhere, then you can put all the irreducible back. It become a factorization of irreducible. Okay, no? Yeah. If it stopped somewhere, then that is the product of irreducible form already. Okay, so if it is not, then you can continue to split it. Make sense? Okay. All right. Right. So we're gonna go to the UFD form here. Stronger theorem here. So in a PID, any non-zero elements, okay, we know that it can split into irreducible, right? So what's the relation between primes then? Okay, so it can be factorized as, let's call this element A. A equals to U times P1 up to Pk, where U is a unit. So meaning you can pull an unit out from an irreducible, and then the rest are the prime. Okay, the rest are the prime. Correct or not? Correct or not? In the prime number factorization, let's say 2 times, I'm sorry, wait, let me think. What number? Let's say 14. 14 equals to 2 times 7. Don't forget, you always have a times 1 there. Okay, yeah, times 1 there. Yeah, or you multiply -1 times -1 also can. Okay, so these are unique. Okay. And moreover, actually, this factorization is essentially unique. Okay, the choice of these Pi up to Pk is unique. Okay, can you write 2 times 7 in different way? 7 times 2. Commutative, right? Is the same, right? Okay. So it's unique. So in what sense here? So in the sense that if you can write it in the other form, let's say U equals to P1 and P2 up to Pk equals to V times Q1 up to QL. Okay. Actually, the number of terms you need to use is the same. Okay, so this K and L have to be the same. How about relation between each Pi and Qi here? So you can rearrange them. Okay, we can rearrange them because we are commutative. You can rearrange them such that we have room to play here. You can write Pi as a unique time Qi here. Okay, this is not too counterintuitive. For example, 14 equals to 2 times 7, right? But obviously, -2 times -7 also works. Okay, it could be differ up to a unit. Does it make sense? Okay. All right. Should we prove this? This proof is a very standard uniqueness proof in algebra. Okay, so very, if you see some statement that you need to prove about uniqueness, rearrangement, this is the standard argument here. Okay, so let's show you the standard argument. Proof. Okay, so we just prove what? In PID, how can we factorize our elements? Just now we just proved, right? We can factorize it into what? Who I haven't asked yet. Jia. In PID, we have a factorization of elements into what? Based on the previous proposition we proved. The word start with I. So based on what we have proven just now, every element in PID has a factorization into what sort of element? This one we haven't proved yet. The one we have proven. This is what we're gonna prove. We want to factorize it, further factorize it into unique type primes. But before that, what did we prove? Product of what? Start with I. What's the word start with I? Yes. Okay, so we start with irreducible. Okay, so let's split our factorization into irreducible first. But in this case, our irreducibles are prime. Okay, our irreducible are prime actually. Okay, so automatically we have a prime factorization now. Okay, at the start we prove right irreducibles in PIVS. Okay, so well now actually you can use the irreducible element here to write out the factorization of A, so call it A, right, into unit times some primes. Okay, because irreducible are prime. Okay. So it's not too far going from irreducible to prime, based on what we have proven. But now it's about uniqueness. Okay, about uniqueness here. So how about uniqueness here? Well, so there's some trick here. Either you see before, or either you think about it before. So suppose you can write out two forms of different factorization of A. Okay. So well, there's not much property you can play here. What you know is just U is unit. You put a bunch of unit together, and then you have a bunch of primes. Okay, so you basically you need to use prime definition here. Okay. Well, since PI is prime, right? Okay, PI is prime. So what can you see here? Okay, before PI is prime, can you see that? Let's take, should we start with PK? Okay, let's start with PK. So PK should divide the right hand side, right? Because you write the right hand side as a multiple of PK. Okay. Does this make sense? Make sense? Makes sense. Okay, because you can write the right hand side as a multiple of the factor in the left hand side. But PK is prime, right? Okay. PK is prime. What's the definition? It divides one of the QI. Okay, so PK must divide some QI. So let's say QJ, where J is in between 1 and L. Okay. So therefore, PK could be written as a multiple of QJ times W. Should this W be unique or not? Let's put it this W in a ring first. Is this W a unique? Match the proposition, right? I mean the statement in the proposition, we hope that this is a unique, right? Then we will be happy. For now, it's divisibility, okay. Is it a unique or not? Is it a unique or not? What's the property tell you something is a unique? Sorry? Louder a bit.
Yes, because
Why? Why integral domain give you unique? Let's write down what you say. You say PK equals to QJW1. And then PK equals to QJW2. Something like this. And then you want to take a difference between them. So you write QJ times W1 minus W2 is 0. Where's the unique telling you? This is not additive inverse. This is multiplicative inverse. This unit. You just show that the unique have to be, you just show that the inverse, not inverse, you just show that the WI is unique. Unique. Is it a unique? Yeah. Is this a WI a unique or not? Yeah, because this proposition tells you that PI and QJ differ by a unit. There's one property will tells you something is a unique, right? Irreducibility or prime. Irreducibility says what? Okay, A equals to BC or AA divided by BC. A to BC implies that B or C is a unique. Okay, but we know that primes are irreducible, right, in integral domain. So you write an irreducible element as a Qj times W. Since Qj is a prime, W must be a unique. OK， 哇，很好用哦 ，Jack， 已经回答好3次了。There is a unique W in R. Okay. Since EK is irreducible. Okay, then what happens here? Then what can you see here is if we write out the product again, we make it PK. So let's say up here until PK minus 1 with PK. So here become QJ times W equals to V times Q1 blah 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 QJ blah. Where's QK here? Some J, I call it some J, right? Okay, here. So here, this two will cancel out. Okay, then you can play this game. Okay, one by one. Yeah, no. Okay, so you can play this game continuously. Then by induction, you can keep playing this game here. Then you will get that Q must be equals to L. Okay. Okay, no. You cancel one by one. Any question? Any question? Okay, so before we go to next part, so this will motivate a definition which we call UFD here, unique factorization domain. Okay, so unique factorization domain is basically just the property we have proven just now. It is an integral domain R such that you can write your A into some unit multiplied by some primes. Okay, so basically what we have proven is a PID is a UFD. Okay. Okay, one thing to note here, there's no uniqueness statement here. There's no uniqueness statement here. I didn't say that all this factorization has to be unique. But it turns out that if you define like this, it is unique. How to show? It's the same property we proved just now. Okay, it's the same way we proved just now. So the uniqueness comes from the prime. Okay, if you can write it as a product of prime, you are unique. Okay, no? I don't need to claim this is unique, but the property of prime is unique. Does that make sense? Okay. Other hand. Okay. Any question? So what I want to tell you is the nature, okay, of your construction is very important. Okay. If your construction is good, there's a lot of nice property will drop out, okay, without any extra condition. Yeah. So the proof just now, we just use that the decomposition is using prime and use the prime definition to show that it's unique. Okay, I didn't need to specially mention that all this decomposition must be unique. Okay. Okay, so you should do the sanity check again. So meaning the factorization is essentially unique. You no need to impose the uniqueness. No need to check, meaning no need to check that your decomposition is unique. If you can write it as a product of prime, you are already okay. You can prove it in general. Just using the prime elements property here. Okay. Any question before I take a break? Where's Eugene? Anyone know where the Eugene is? Eugene. Is he still around? Eugene is in which group? Which group contain Eugene? Your group is your group member okay 吗？OK 问一下，周末没有来上课？OK. Alright, so let's break until 106. Hey Junhong, have you guys decided when to meet?
Because not together then different heading. Yeah, and then sometimes you don't reply also.
Who didn't reply? Write into the report. If who didn't reply, write into the report. Yeah, make a rule that they need to reply. Yeah, if whoever don't reply, you write to a report. And then see how.
I get them to meet after class.
Can.
Yeah. Yeah. 我也有个问题，
什么问题？
你 assignment 的第二题的 A 能不能给点 assignment 第二题给点 hint 好不好？
对呀，我去想看。
我昨天跟 Ryan 和文川讨论，发现你们一个人都没有想。
OK，我回去看看，我回去看一下可以给什么 hint。
哦，
耶，
但他们为什么定义 irreducible 和 prime 的时候一定要它不是 unit？
啊，
就说一定要一个数存在。
我看一下啊，因为它是 unit 的话，
会造成什么结果？
我想一下，应该是没有什么太大用处诶，给 unit 啊，给我看一下。如果 irreducible 这个东西给 unit 会发生什么事情啊？对啊，如果把 unit，I mean 它这个肯定符合嘛？你可以把 unit 拆成不 unit 吗？不可能的，你应该不可能把 unit 拆成 product 不是 unit 的东西
那我觉得
啊？不可能的，就没有好讨论了。有可能咩？如果你分开没有 multiplicative inverse，为什么乘起来就有 multiplicative？我想一下，有这样的事情发生，
进去里面还有这样。
不可能
它是那个要求嘛，就是你要是在 integral domain 和 PID 嘛，
对啊
就是避免了这种情况的发生。
就没有就讲说一个
有点 irreducible 啊，
一个东西
是吧？
，irreducible 或者 prime，就为什么我们两个 assume 它不是
为什么一定要 assume 它不是 unit？
啊，什么意思？这么要问会
没有，他是问这么 irreducible 个 prime，它是 define on 它不是 unit 的情况下，
如果它是 unit，会有
它是 unit 的话，a 乘 a 负 e，那么 e 就是
A 负 E B C，
e 就是 irreducible 的，e 就是 reducible 的，因为 e 就是你 a 乘你 a 负 e，a 和 a 负 e 都不是，诶，没有 a 和 a 负 e 都是 unit 的，e 也是 unit 乘 unit 的，那也是。是可以嘛？你可以把一放进去，
不是 I mean like 也是因为我想想看啊，是 unit 会发生什么事情？
肯定能拆成两个 unit。
unit 可以拆成两个
我感觉
unit，
unit 要拆
一等于减一乘减一，
它的 claim 就是 unit，如果拆成两个的话，一定每个都是 unit。
哦，应该要
我感
对
觉会是
对是要这样子的。
prime 不能 prime，如果你把 e 变成 prime 的话，那么在这个 factorization 的定义会出问题。factorization 这个就变得很没有用了，因为你就可以随便加几个 unit 装到 prime 进去。所以你的 prime 你要做一个有用的 prime 的话，prime 不能把 unit 当成 prime。你可以这样定义的，这样定义出来的那个 unit prime 就没有什么用了，就是不能讲 factorization。就等于一乘一乘一乘一乘一乘一乘一就无限个 prime。然后
对不？
什么？你在讲 prime 还是在讲
还是问能不能把那个
prime 加上 unit？
这个 definition 为什么需要设置不能是 unit 嘛？
你现在是讲 irreducible 还是讲 prime？
没有，因为 OK，其实两个是一样的。如果你 prime 放 unit，prime 就没有用。可是你在那个 PID 的情况下，prime 和 unit 又是等价。所以如果你允许 prime 可以放 unit，
没有 prime 和 irreducible 等价，
那 prime 和 unit 是不等价，对。
所以是 PID 里面。
所以在 PID 里面，如果 irreducible 有 unit 为定义的话，那么 prime 也要有 unit 为定义，那么这个 factorization 就没有用了，因为就
不一定能够变成 unit。
没有 unit 的，没有唯一的 factorization，因为
有可以
可以乘无限个 e 啊，你可以乘无限个 unit。
对对对，只是我想说，为什么它的 definition reducible prime 就一定要有那个 assumption？
为了让后面的东西变得好看一点。
为了变好看不是呢？还是真的是有我很奇怪？
不是他刚才讲的那个东西应该有用哎。如果你要拆 unit 的话，应该就是 unit。
我感觉应该是。
一定是，因为
为什么会这样子？就不
因为
能一个不 unit 吗？
假如我们讲这一边是，
你想
一定是吗？
是啊，
一定是吗
？unit
？unit 的定义就是它有逆元素，可以把它变成 e。
对。
那么假如我这一边是 a 的话，a 等于 bc，a 有逆元 那 BC 一定有逆元吗？
整个一定有啦，
你 C
整个 product 一定有。
怎样讲？C 等于AB 的话，这样子你 C 乘 C inverse 是 E 嘛？这样子这个 AB 乘以 C inverse 是
也是
E， 所以 A 的 inverse 是 BC inverse，然后 B 的 inverse 是 AC inverse。
除非就是 B 或 C 是 E，然后就 favor 了。
喂，什么？如果 A 是 unit 的话，A 写成 BC，然后
然后这样子 B 的 inverse 是CA inverse，然后
我想一下
C 的 inverse
，C
是
的OK，啊，对，这样就可以 prove 到。
是可以这样定义一个新的有 unit 的 irreducible 和有 unit 的 prime，应该是这样定义一个没有问题。
那什么
没有，这样 B 跟 C 都是 unit 啊。
对啊，
真的没有，好像没有用过。
那就像在整数里面没有人会把一叫质数一样。
对，就变得没价值。
没有，它是把因为 A invertible 了嘛，
对
那你 A invertible 可以丢前丢后面嘛，丢前面就是 C 的 inverse，丢后面就是 B 的 inverse，
哦，对，
因为考虑的
它就 invertible 了，
对，
就没有用，
就是
有什么用？
就你一个会拿成一雷 D 或一雷 C 的嘛。
一等于 B 或一等于 C。
irreducible 的定义是这样的，假如是如果 A 等于 BC，B 要是 unit 或者 C 要是 unit。现在如果 A 是 unit 的话，B 也是 unit，C 也是 unit，所以 technically 你是可以当成是个，它有符合 irreducible 的定义
应该是 A 等于 A 是 unit 等于 BC，这样 BC 是一个 unit，
的。
要看整体的。
如果 A 是 unit 的话，BC 就是 unit。
如果对，
那你就怎么讲 B 是 unit 和 C 是 unit？
因为我把 A 负 E 给乘出去的话，E 就等于 BCA 负 E。
对，
那么 CA 负 E 乘上 B 就等于 E，
你找到他们的 inverse，
所以 CA 负 E 就是 B 的 inverse，所以 B 就会是个 unit。
对，所以两个一定要是 unit 的。那如果两个是 unit，会发生什么事情？
不能发生什么事情，就你把 unit 分成 unit，然后 unit 吧。但是这个东西是不能拆成 product of unit，
哦，这样就 quadratic 啊，
看到点？
一两个都是 unit。诶，也可以啊，
可以，但是所以它才加多另外一条东西。因为如果它是 unit 的话，
一定
你就是拆成 product of unit 就这样啊，就没有什么特别了。特别的是这个东西不是个 unit，但是它又可以拆成一个 unit 层。
全部 unit 是 irreducible 的。
不可以这样想，因为 irreducible 已经包含不是 unit 了，所以你不要这样想。你要想的是这条东西嘛，这条东西没有名字，你可以给它名字。
在里面删
不要
掉。
给他名字。
你要给它名字也是可以的。
他说你忘了干，太漂
漂亮，很重要。
不是那个，
等一下
是你讲。
Alright, let's continue. Okay, so from what we have proven just now, right? If your ring is an integral domain and then satisfy this kind of property that PID satisfy, actually is a UFD object already. Okay, so we take this property as a defining property for the UFD. Okay, and obviously, you should also expect that every irreducible in a UFD is also prime. Okay, so similar proof, so we just leave it. You can try and write it out. And next, we're going to prove that our goal is to prove that R adjoint X, if R is a UFD, R adjoint S is also a UFD. Okay, a polynomial ring is a UFD. Okay, so to build that stage, so let's write down the motivation first. So the motivation for the next part is if R is a UFD, then you have a decomposition into prime, then the ring R adjoint X is also UFD. Okay, so we're gonna prove this. So it's the then so is the ring R join X. So this is our final goal for this part here. Okay, so to do this, we'll introduce one more piece of definition, which is called primitive polynomial. Okay, so what does a primitive polynomial means? Actually, the definition is very intuitive. Okay, so intuitive, what do I mean by intuitive here? So here you see that we introduce irreducible, prime, primitive. Okay, so be sure that where these adjectives apply to. Okay, does it apply to a ring or ideal or what or polynomial? Okay, don't mix up. Prime is not primitive, and it's not irreducible. They are not the same, all of them. Okay, they are equivalent. Okay, in some ring. Okay, but they are not the same. Okay, so primitive says that if the GCD, okay, GCD of its coefficient is 1. Okay, do you know how to make this primitive polynomial or not? You just distribute the common divisor. You just pull the common divisor out and then throw it away. Then you can make a primitive polynomial. Correct or not? Okay. So one lemma is called the Gauss lemma. Okay, so whenever people put a name beside lemma, meaning that this lemma is not that trivial. So maybe they thought that initially it's quite trivial because this statement really trivial. Product of primitive polynomial is primitive. Okay, product of primitive polynomial is primitive. Should expect it to be true. I don't know. Okay, I give you 3 minutes, see if you can think of a proof or not. A primitive polynomial is primitive. Actually, there's a lot of lemma bearing Gauss name. I think number theory you also see Gauss lemma. What about all its formula there? From Gauss also. Okay, let's quickly go through it. Actually, this proof is not tricky. It's not really tricky, but let's see. So, well, obviously, you need to start from a product of primitive polynomials. So let's write down 2 pieces of polynomial here. And then you want to show that the product also have GCD of coefficient equals to 1. Okay, so that is your goal. Okay, so that's your goal. Both of these are primitive. Okay, so what you do is take a prime P, and since the GCD of these AI and BI are equal to 1, right? So for sure you can find IJ, you can find the largest one, such that P doesn't divide AI and P doesn't divide BJ. Okay. If can, then this P is your common divisor, and non-unit common divisor. Unit, I mean, equals to 1. Then I want to argue that there's some coefficient in the product is not divisible by P also. Okay, so which one? I think you should look for the obvious one. Okay, the obvious one is the I plus J coefficient. Okay, so let's call it C J I plus 1 of the product of FG. A5 is not here also, huh? Here. Is it here? Not here, huh? Okay. Just realize. Okay, so what's the Ci plus J component here? How do you like distribute your coefficient out? What are all the terms here? Summation of what? All the degree that add up to I plus j. Correct or not? Okay, so what are the possibilities here? So I will split into 3 groups. Okay. So obviously AI bj is in here, right? Xi times xj is si plus j. And this other group, AI plus 1, bj minus 1, correct or not? The degree is I plus j. And then what else? AJ plus 2, BJ minus 2, and then so on. Okay, you can go higher A. Similarly, you can go lower A, lower I, right? AI minus 1, but increase in BJ plus 1, and then so on. Okay. So why do I do this? Actually, this is the sum of AI BJ and the terms divisible by P actually. Correct or not? Is all the rest divisible by P? AI is the largest I, doesn't divide. So all the I below here is the largest AI doesn't divide. So all the I after I, all the J after I must be divisible by P. The other cases, Bj is the largest J doesn't divide. So for all the K greater than J, P must divide Bk. So the second terminal also divide by. Okay. So the only thing that P doesn't divide is AJ times BJ. Okay. Yeah, so as P is prime, P doesn't divide AJ, BJ. Okay. And so it doesn't divide the coefficient. Okay, since P is arbitrary, then we're done. Okay, no. So actually, we rely on the assumption to find this A and J. We rely on the assumption that both of them are primitive. Okay, we can find such I, such J. Okay, if we cannot find, then this P is your common divisor other than 1. Okay, no. Does it make sense? Here's number 1. Hello. Does it make sense? Okay. You can find some AI, BJ cannot divide. If you can find, that means this P will divide all of them. If you can find, then this P is one of your common divisor, which is not 1. Okay. Okay. Okay, next. There's some very straightforward lemma here. Let's put down a lemma. So let F be a field of fraction of a ring. Okay, so why we bother introducing a field of fraction here? Because we're gonna divide. We're gonna divide by some element inside the ring. Okay, so the natural place to look for this inverses, okay, is the field of fraction. Okay. So if first statement is if U is a unit in R, then U is also a unit in RS. Is this obvious or not? Is this obvious? If it is unit meaning what? You have a multiplicative inverse in R. But R also sit inside R adjoint X. So your multiplicative inverse is also there. Okay or not? Hey, if this is not obvious, something wrong with your understanding here. Because R just sit inside Rx. Every element in R is an element in Rx. Yeah, this is the only thing you need to know about the statement. Okay. And then second, if P is a prime element in R, then P is also a prime in R join X. Okay, so you can try and prove this left as an exercise. Maybe we'll do the last one. So the last one is if fx is a primitive polynomial R join X, which is at the same time irreducible. Okay, so it is prime in the field of fraction adjoint X. Okay, then we can say that it is actually prime in R join X. Okay. I think in A2 also got this kind of checking on divisibility. You check on Q adjoint X and then you deduce in ZX. Yeah. Okay. So let's try the third one. 1 and 2 just left for exercise. Let's try the third one. All right. So you want to show something is prime, right? So how do you start? Prime definition. Second hour. Prime definition again. Suppose f x equal or divide. Divide. Okay. Gx and hx in Rx. What we're gonna show is f either divide g or divide h. So that's our goal. Either f divide g or f divide h. Okay, cool. So now you see our assumption concerning f prime, big F field of fraction. So let's discuss this condition there. Okay, so by assumption, since it's divisible by Rx, right? But we know that this Rx should sit inside Fx. Okay, so obviously F will divide GH also. Okay, in Fx. But we know that in Fx there are more property to hold, right? It is irreducible. It is already prime. Okay, so meaning what? So F either divide Sayed. Since F is prime in Fx, so F either divide G or F divide H. Okay, there are two possibilities here. Okay, so you can see that this argument is how to say independent on the labeling, right? So let's assume one of the cases happen. Okay, the other cases can be argued similarly. So without law of generality, G divide H divide G. Okay. So what does it mean by H divide G? We can write it as a multiple. Okay, multiple of element in Fx. So G equals to Fk. Okay, here now is the trick. Here's the trick why we use field of fraction already. Okay, here's the trick why we use field of fraction. So since these elements, we view them in Fx, right? Field of fraction here. So the coefficient you should imagine we could have denominator, for example. Yeah, for example, we could write G equals to AG prime, okay? And then K equals to B over C K prime. Okay, so what are we doing here? So all these ABC is to make G tilde and K tilde primitive. So like what I said just now, you pull out the common divisor. Okay, you pull the common divisor out. Does it make sense? Make sense or not? Need example. For example, 2x minus 2 equals to 2 times x minus 2. Okay, pull the coefficient out. Okay, but in the K part, I try to write it including the denominator because this K live in the field of fraction, right? So instead of field of fraction, what do you have? You have, for example, one if the field of fraction of z is you have 1 over 2. Okay, I pull the 1 over 2 out. Okay, so the A, B, C, all the numerator, denominator, all of them is R. Okay, and then B over C is in F, for example. Does that make sense? Okay, so let's use the primitive property here. Then what can you see here? Then what can you see here? We actually see that AG prime is equals to B over C FK prime here. Okay, which implies that if you move the denominator around, you will get this equality. Okay, now we are going to use our assumption now. What do you know about G prime, F, and K prime? That has a similarity here. G prime, K prime, we construct it as a primitive polynomial. F, F is what? F is a by assumption primitive. Okay, so note that as F prime, F, G prime, and K prime are primitive. What can we say here? Gauss lemma says that product of primitive polynomial is still primitive. Okay. So by Gauss lemma, we can actually equate the not the coefficient, the common divisor that we have pulled out. But they differ by a unit. They could differ by a unit. Okay. They are equivalent up to a unit. Okay. So in this case here, we can cancel out the factor such that we get G tilde equals to U times K tilde. So if you put it back, what happens here? If you put it back, you can write G as AG tilde as A times U times F times K tilde. But what does this mean here? This everything here happens in R actually. Okay, everything here happens in Rx. Why we move to Hx? Because we scared that your coefficient has denominator. Okay, but we play around, we move the denominator to the other side, we have an equation back in Rx. Okay. And then the act of pulling the denominator also makes K tilde live in Rx. Correct or not? Does it make sense? Does it make sense? For example, I give you an example. 1 over x plus 1 over 4. What can you do here? You pull 1 over 2 or pull 1 over 4. You can pull 1 over 4 such that you get 2x plus 1. Okay, sitting back into Rx again. So this is the part that we wanted to live in Fx so that I can pull the fraction out. Okay, so this everything happening in Rx actually. So what do we have now? So you can see that F actually divides G. okay, with the multiple of AU. Okay, does it make sense? Okay, so if F divide G in Fx, we prove that F also divide G. Okay, if F is primitive, and irreducible and M prime in Fx. Okay, so there are quite a few properties here. Okay, so F is prime in Rx. Okay, so we have go all the way from you see from F divide G in Fx to F divide G in Rx, and then where we use the Fx technicality here actually is this part, and then we move it back to Rx again. Hey, Faris, you just arrived. What happened? Misscheduling? Oh, okay. So where were you? Huh? Oh my, your home. Where's your home? Your room. Oh, you forget the time. Okay. So how you figure out the time in the end? Ah, you see, message in the group is important. So make sure you message your friend if they don't come. Okay. Otherwise, you cannot realize. Okay. Okay. So let's go on. Theorem. Okay. Now we will prove this theorem now. So if R is a UFD, then so is R adjoint X. Okay. So imagine this statement is very pretty powerful. If R is a UFD, RS is a UFD. RS why? Still a UFD because RS is a UFD ma. So RX adjoin Y still a RF UFD. So you can keep adjoining finitely many variables. Still a UFD. How nice. Then later I'll find algebraic that will be on K adjoin X1 up to some extent. Okay. This is the setting we're gonna use. Here's the affine space setting. All right. So how are we gonna start this? Okay, so what to do here? Well, obviously you need to take some polynomials inside your Rx. Okay, we want to show that it can be factorized into a unique factorization based on prime elements. Uniqueness is what you don't need to prove. You just need to prove existence, I guess. Yep. Right. So what to do here? What's the idea here? What can we do next? Just now we involve fx, right? Field of fraction. Okay. So should we introduce the fx at some point here? So just now I already said that Rx will sit inside fx, right? By embedding. Fx, why we study fx? What do you think? Any other reason or not? F is a field. Huh? Field adjoint X is what kind of domain? Integral domain for sure. More than that. Yes. Principal ideal domain. Principal ideal domain are, just now we proved that, are UFD. Okay. So if you put this F into Fx, then we can factorize it into irreducible. Okay. If we put it into Fx, it is irreducible. Okay, because F adjoint X is a PID, and therefore UFD. We are not sure what happened in Rx, but in Fx, you can split because F adjoint X is a PID. If you're not sure, you need to prove it. Yeah, I think this is some statement that are proven in AA1. Okay, if not, you need to revise it. All right, so actually similar technique, okay, similar techniques. So we will try and pull all the common divisor up. So we just consider the irreducible. We will further assume it is a primitive polynomials. Okay, so how do we do this? So let's write down for you. So how are we gonna do this? Not this R, it's the usual R. So we will write our fx as R over X. Okay, we pull all the divisor up such that all this irreducible is already primitive. Okay, is it simple to do? Once we have irreducible, I just pull out all the common divisor. Make sense or not? Okay, such that all these GI is not just irreducible, but also primitive. Okay, I pull the coefficient up. I mean factors. Okay, at the same time irreducible. Okay, so it is irreducible there, obviously. Is it obvious or not? So I'm going to claim that this GI is prime in Rx. What's the irreducible property and the prime property relation again? Which one imply which? In what setting? In integral domain setting, which imply which? It's the last hour proof. In integral domain, which imply which? Prime imply irreducible. Okay. In a PID setting, irreducible will imply prime. Okay. Okay, so in the PID setting, but irreducible implies prime in integral domain setting, is it? Okay, yeah. So we are in integral domain, so we are good. Okay. Right. What else? Same. On the other hand, we could just write down fx equals to a times some primitive function. Okay, so meaning I just pull out the common divisor of f. Just now I pulled out all from qi. Now I just pull out from f. Okay, such that I write it as a product of ring elements times the primitive elements here. So what? So again, we have two expressions on both sides. Okay, so similar technique just now, because product of primitive is primitive. Okay, before that, let's make it into some statement inside R adjoint X first. Okay, so you can see that a similar technique is used. So as we know that all these are F prime, GI are all primitive. Then there's a relation between their common divisor here. So they are equal, but equal up to a unit. And they could be equal and then equal up to a unit. So, so what? So then we substitute this relation here back to our F, which we see that F is equals to what? R over X, right? R over X of G1, G2 up to Gk. But we know that our R is UAX. So you can see that this relation helps you to cancel out the denominator. And then you stay back in your R join X here. Okay, now. Okay, so you have written what your F as a product of prime numbers. Sorry, prime elements. Okay, prime elements, but maybe okay. So let's list down what we have. Here is prime, right? Okay, but here is a unit, right? You might ask me, what is this guy doing here? What's this guy doing here? Where is this from? Where's this guy going here? This guy from where? This is from the divisor of f, right? The divisor of coefficient of f. Okay, so in particular, this guy live in where? Where does this guy live in? R. But R is a UFD. So you can further split this R into prime in UFD. Does it make sense? Okay, so you have split everything into primes. Okay, no. Where we can further split A into V times A1, A2 up to AL since R is UFD by assumption. Okay, because the coefficient ring is a UFD. Okay, so we have split our F into unit time all the primes. Okay, no? Any question? Any question? If no question, I can continue. Let's continue some more. Any question or not? I already split my F into product of primes times unit. This is the UFD definition. Okay, no definition and no question, then we continue. So next, we'll introduce an R algebra. Okay, so now we will introduce some language on R algebra. So just now what we discussed was what we discussed all along is integral domain, okay, PID, UFD. Okay, now we go to R algebra. So okay, so maybe do some motivation here. Okay, so how far have you gone to here? So, well, if you start with A1, you have groups, right? So either you have plus or multiplication. But when you go into ring, you will have both of them together. So how do I write both of them together? Put like this, maybe this one like this. So we try to put two operations together. But algebra, so algebra actually has the third property here, which we call the scalar multiplication. Okay, so actually you have seen this algebra before. Well, I mean, high school you also see algebra. When people talk about algebra, what is the algebra? What's algebra there? 2x, right? X plus y, xy. These are algebra. Why are they algebra? Do you know? Or you just see xy, or xy is algebra? You know why? Because you have scalar multiplication here. You have addition here. Okay, you have, let's say this one, multiplication. Well, these are algebra. Algebra is these three things here. Okay. The other algebra you saw in first year is the matrix algebra. Correct or not? Can you add matrices? Can you multiply matrices? Can you multiply your matrix with a scalar or not? Okay, so this is algebra, matrix algebra. Okay. So what's the definition of R algebra here? So if R is a ring, then an R algebra is defined to be a ring. Okay, this is a bit fancier definition here. Together with a homomorphism. Okay. A homomorphism alpha from R to A. Okay, so you got two ring actually, two ring interaction. Okay, there are two ring interaction. Call it R. So this R, you should think of it as your scalar. So you tell me how scalar act with the other ring. So you have a scalar ring, you have a ring. So how scalar ring acting on this ring from an algebra. A usual homomorphism here we take is just inclusion. The usual one we take is inclusion. For example, a real number is an algebra, right? Okay, so it's a R algebra. Okay, so I give you an example. So for example, R is a R algebra. Okay, so what's the homomorphism you take here? It's just the inclusion morphism. So the homomorphism here we're referring to ring homomorphism because both sides ring. Okay. So it's just something extra than ring algebra. It's the scalar multiplication. Okay, but the scalar multiplication here is really just the real number multiplication, right? It's just real number multiplication. Okay, you can't really differentiate 2 times 2 and 2 times 2. Cannot really differentiate because we define it to be just real number multiplication. Okay, but if in the other case it's different also, if you take 2 times the matrix, right, it's different. But if the matrix times matrix, it's different definition. Did you realize that these two give you the same matrix? I didn't realize it. Let's see, no one, I didn't use some swap. But this is the two different ways to get this 2002. One is scalar multiplication, one is matrix multiplication. Do you realize or not? Okay. Okay. Right. So I'll put a remark here. So basically, an R algebra is a ring with scalar multiplication in R. Yes, scalar multiplication. All right. So we have algebra, right? Obviously, next thing is talk about function between terms. Okay. So we'll define what is called R algebra homomorphism. Okay. So this is an algebra homomorphism. So we have learned group homomorphism, ring homomorphism. So now it's a R homomorphism. Okay. So, well, since we talk about R algebra with the homomorphisms, okay, then we need to include this into our definition. Okay, so depend on homomorphism. Although you have real number over R algebra, right? If we change the homomorphism, then you will change the R algebra also. Okay, so it really depends on the homomorphism, how you interpret the scalar. Okay, so well, so what's the map between A to B? This is called the R algebra homomorphism, or sometimes we call it homomorphism of R algebra if phi is a ring homomorphism. Okay, actually it's just a ring homomorphism and satisfy this phi composed with alpha equals to beta. Okay, so this is a commutative diagram. So what's the commutative diagram here looking like? So you have a R go to A, okay, using alpha, and then go to B using beta. Okay, and then phi is a map from A to B. Okay, so you want this diagram to commute. Okay, phi alpha. Does it make sense? Okay. It has to commute, right? Otherwise, the way you interpret R inside B could be different. Then you will have a trouble. Okay, meaning you are mapping to the other R algebra B or not this B, different B or because it doesn't match with how you interpret the scalar. Like this beta here. Yeah. All right. No one here yet. So let's quickly continue first. So we say that and R algebra A is finitely generated. Finite generated over R in this case, if there exists some intermediate, A1 up to AN with A equals to I shouldn't write equals, right? I should. Can I write equals? Yeah, I think I can write equal. Can I write equal or not? Right. So where are these A1, AN come from? They are not intermediate actually. They are actually coming from A, right? Such that I can write A equals to not isomorphy is equal to R adjoint A1 up to AN. Okay. So everything can be written as a linear combination of this A1 up to AN. Not linear combination, or we can take a product of AI squared. Yeah. So this is some form of a similar idea of vector space. If it's vector space, then these are the bases, but these are generators. So the difference between basis and generator is basis linearly constructed. Okay. You just can take linear combination. But in this case, yeah, you can take A1 square, A1 cube. So it's a generator. So here, you can. So in basis, two operation you can take: scalar multiplication and addition. But here, there are three operations you can do: scalar multiplication, addition, multiplication between elements. Alright, so that's why A1 square are included. Okay, last. Someone waiting outside already. So, an algebra is finitely generated if and only if let's say call this A is isomorphic to R adjoint. So this is an R algebra. R adjoint x1 up to xn over I. Okay, so for some ideal. This proof was just left for exercise. This is like the ring exercise here. Okay. So you can think of that before quotienting by the ideal, right? Already finally generated, right? Now you should think about why I take away ideal, still finally generated. I equating more things together. Should I be even more finally generated? Or equally finally generated? Or will you increase generator? It will be in trouble, right? The generators. Okay? It could be equally finite generator. Could be the same element. Okay. Let this for exercise. Let's see. 1, 2, 3, 4. Okay. I think about 9 slides like that. For next part, we will cover up to algebraic close. Okay. After that, we will jump to R5 varieties. Okay. See you tomorrow.